Hello everyone, this is Autumn Bauman, and today I'm going to be demonstrating my Physics 212 project, Coulomb's pendulum.
The electroscope was invented in its modern form in 1731 by Abraham Bennett. Two leaves are electrically connected, so when charged, the leaves of the electroscope separate due to the repulsion of like charges. This repulsive force can be modeled with Coulomb's law.
The goal of my project is to measure the static charge stored on two spheres. Initially, I plan to do this by use of a device similar to an electroscope, where two spheres would be charged to equal amounts via a Van de Graaff generator, and then the repulsive forces would be measured between them. Sadly, this did not pan out. I suspect this was due to environmental factors, including my inability to electrically isolate the system and air currents. Since I was using a Van de Graaff to charge the spheres already, I realized there was a much simpler way to do the same experiment. A Van de Graaff uses the triboelectric effect in order to generate a high potential difference between two surfaces. In the experiment, I connected the hanging sphere to the base of the Van de Graaff generator.
The main construction involved in the project was the hanging metallic sphere, which I built by coating a ping pong ball in aluminum tape.
From there, electrically isolated the system. I measured 1. the length of the metallic thread, 2. the center-to-center distance of the spheres, and 3. the mass of the hanging ball. I turned on the Van de Graaff and allowed the system to stabilize. An issue I encountered was the ball moving chaotically back and forth. In order to deal with this, I used my calipers to move the sphere past its equilibrium position, supporting it fully, and then retracting until the electrostatic forces were able to fully support the sphere. This gave me reasonable accuracy within plus minus 0.1 millimeters. I did 4 runs and averaged the displacement. I was able to find a deflection to be on average of 39.4 millimeters. I was able to create this free body diagram of the system, which can be rewritten as this similar triangle to make solving easier. We find that the tangent of theta is equivalent to the electrostatic force divided by the gravitational force. From there, we can rearrange it to find that the electrostatic force is equivalent to the gravitational force multiplied by the tangent of theta. Finding theta is simple, just simply using the measurements of the physical triangle and the arcsine function in order to find theta to be 11.62 degrees. Putting this all together and plugging in the numbers, we find that the electrostatic force is equivalent to 0.00867 newtons. Because both objects are spheres, we can model them as point charges and then use Coulomb's law, rearranged as shown, in order to find the charge stored on each. For the radius between charges, we simply subtract the average displacement of the charges from the radius from center to center at rest. That leaves us with a charge-to-charge radius of 0.2176 meters. Plugging in all of those values, we find that the charge stored on each surface is 2.13 times 10 to the negative 7 coulombs, or 213 nanocoulombs. This experiment is by no means perfect. Some charge is stored in the wires, which connect everything together, and since we are not in a vacuum, air currents will impact the stability of the system. Further, the system is not fully electrically isolated, so there are going to be charge imbalances between the two surfaces. Finally, my measurements were all done by hand, which will lead to greater inaccuracy. In conclusion, while this experiment was by no means perfect, I feel it served as an excellent and fun demonstration of electrostatic forces and Coulomb's law.